Welcome to Loops and Loops, your guide to the intricate world of computer organization. Computer organization delves into the fundamental principles underlying the design and architecture of computing systems, shaping the very backbone of modern technology. Join us as we navigate through the complexities of computer organization, unraveling the inner workings of processors, memory systems, and input-output devices. Whether you're an aspiring computer scientist, a tech enthusiast hungry for knowledge, or simply curious about the inner workings of the machines we use every day, you're in for an enlightening experience. So tighten your loops, prepare to delve deep into the heart of computing, and let's explore the fascinating world of computer organization together. Computer organization refers to how a computer's hardware components are structured and interconnected to perform tasks efficiently. It involves designing and organizing these components to ensure smooth communication and coordination, ultimately leading to the effective functioning of the computer system. Understanding computer organization is crucial for optimizing performance, managing resources, and enhancing overall system reliability. The computer organization differs from computer architecture in that computer architecture focuses on the design principles and logical structure of a computer system, while computer organization deals with the physical implementation and arrangement of hardware components. While architecture defines the overall system's design, organization dictates how that design is realized in terms of physical components and their connections. Abstraction in computer organization involves hiding complex details of hardware implementation behind simpler, more manageable interfaces. It allows programmers and system designers to work at higher levels of abstraction without needing to understand the intricate details of the underlying hardware. Abstraction enables modularity, flexibility, and ease of maintenance in computer systems. The central processing unit is the brain of the computer, responsible for executing instructions and performing calculations. In computer organization, the central processing unit coordinates the activities of other hardware components, fetches instructions from memory, decodes them, and executes them. It performs arithmetic and logical operations and controls the flow of data within the system. Memory hierarchies play a crucial role in computer organization by providing different levels of storage with varying access speeds and capacities. These hierarchies typically include registers, cache memory, main memory, and secondary storage such as hard drives or SSDs. By organizing data in a hierarchy, computer systems can optimize performance by minimizing the time it takes to access frequently used data. Abandonment architecture is a fundamental computer design concept that separates memory and processing units into distinct components. It includes a central processing unit, memory, input-output devices, and a system bus that facilitates communication between these components. In von Neumann architecture, instructions and data are stored in the same memory, and the central processing unit fetches instructions sequentially from memory to execute them. The fetch, decode, execute cycle is a fundamental concept in computer organization that describes the process by which the central processing unit retrieves instructions from memory, decodes them, and executes them. In this cycle, the central processing unit fetches the next instruction from memory, decodes it to determine its operation, retrieves any necessary data, executes the instruction, and then updates the program counter to proceed to the next instruction. Input and output devices interact with the central processing unit in computer organization by exchanging data and control signals through input-output ports or interfaces. These devices enable users to interact with the computer system by providing input such as keyboards and mice and receiving output such as displays and printers. The central processing unit communicates with input-output devices using input-output operations. The instruction set architecture defines the set of instructions that a central processing unit can execute and the format of those instructions. It serves as an interface between hardware and software, allowing programmers to write software that can run on different hardware platforms without needing to know the underlying hardware details. The instruction set architecture determines the central processing unit's capabilities and instruction set, influencing its performance and compatibility with software. Registers are small, high-speed storage locations within the instruction set architecture that hold data temporarily during processing. They serve as the primary storage for data and instructions that the central processing unit is currently processing. Registers play a crucial role in improving instruction set architecture performance by providing fast access to frequently used data and reducing the need to access slower memory. Reduced instruction set computing and complex instruction set computing are two contrasting instruction set architecture design philosophies in computer organization. Reduced instruction set computer architectures prioritize simplicity and efficiency by using a smaller set of simple instructions, while complex instruction set computer architectures aim to provide more complex instructions that perform multiple operations in a single instruction. Reduced instruction set computer architectures often prioritize performance and scalability, while complex instruction set computer architectures focus on code density and ease of programming. Pipelining and parallel processing techniques improve computer organization by increasing the efficiency of central processing unit operations. Pipelining involves breaking down the central processing unit's instruction execution process into smaller stages and executing multiple instructions simultaneously, overlapping different stages of instruction execution. Parallel processing utilizes multiple processing units, also called as cores, to execute instructions in parallel, speeding up computation tasks by dividing them into smaller, independent tasks that can be executed concurrently. A computer's motherboard houses various critical components, including the central processing unit, memory modules, expansion slots, input-output ports, and other essential circuitry. It provides the physical and electrical connections necessary for these components to communicate and interact effectively. The motherboard acts as the central hub that connects and integrates all the hardware components within the computer system. Clock speed, measured in hertz, refers to the frequency at which a central processing unit's internal clock generates pulses to synchronize its operations. A higher clock speed allows the central processing unit to execute instructions more quickly, resulting in faster processing and overall system performance. Clock speed is a crucial factor in determining the central processing unit's performance capabilities, although is not the only factor influencing performance. The control unit in computer organization acts as the brain of the central processing unit, coordinating and controlling the execution of instructions. It fetches instructions from memory, decodes them to determine their operation, and controls the data flow within the central processing unit. Essentially, the control unit manages the execution of instructions, ensuring that they are executed in the correct sequence and directing the operations of other central processing unit components. Arithmetic logic units are critical components of the central processing unit responsible for performing arithmetic and logical operations on data. They facilitate computation by executing instructions. Arithmetic logic units perform tasks such as addition, subtraction, multiplication, division, and not operations, allowing the central processing unit to process data and perform computations. The system bus consists of multiple lines or wires that carry signals representing data, addresses, and control signals, facilitating the transfer of information within the computer system. The architecture of a computer significantly impacts its energy efficiency by influencing factors such as component design, power consumption, and system optimization. Efficient architecture designs prioritize power-saving techniques such as low-power components, clock gating, and dynamic voltage scaling to minimize energy consumption while maintaining performance. Energy-efficient architectures aim to balance computational power with energy consumption, optimizing the use of resources to achieve maximum efficiency. Endianness refers to the order in which bytes of data are stored in memory. In computer organization, Endianness determines whether the most significant byte or the least significant byte is stored at the lowest memory address. Big endian systems store the most significant bit first, while little endian systems store the least significant bit first. Endianness affects how data is interpreted and accessed by the central processing unit and can impact data storage, communication, and compatibility between systems. Operating systems interact with hardware and computer organization by providing a layer of abstraction between the hardware and software applications. The operating system manages hardware resources, such as memory processors, storage devices, and input-output devices, and provides services to applications through system calls. It facilitates communication between software applications and hardware components, enabling applications to access and utilize hardware resources efficiently. The Memory Management Unit is responsible for managing memory resources in computer organization. It translates virtual memory addresses used by software applications into physical memory addresses, allowing the central processing unit to access data stored in memory. The Memory Management Unit also handles memory protection, allocation, and deallocation, ensuring that memory resources are used efficiently and securely. Virtual memory systems enhance computer organization by extending the available memory beyond physical RAM, allowing systems to run larger programs and handle more data than the available physical memory. Virtual memory systems use a combination of RAM and secondary storage to create an illusion of larger memory space. They manage memory allocation, swapping, and paging, ensuring efficient use of available resources. Volatile memory loses its stored data when power is turned off or lost, making it suitable for temporary storage of data and program instructions. Non-volatile memory retains its stored data even when power is removed, making it suitable for long-term storage of data and program instructions. Examples of non-volatile memory include ROM flash memory and hard disk drives. Input devices convert physical actions, such as keystrokes, mouse movements, or touch gestures, into digital signals that a computer can process. These devices allow users to input data and commands into the computer system, enabling interaction with software applications and control of system operations. Output devices present process data and information to users in human-readable forms. They convert digital signals generated by the computer system into tangible outputs, such as text, graphics, audio, or video. Common output devices include monitors, printers, speakers, and projectors, allowing users to view, hear, or otherwise perceive the results of computer processing. The basic input-output system contributes to the boot process in computer organization by providing essential firmware that initializes hardware components and prepares the system for the operating system startup. During the boot process, the basic input-output system performs hardware diagnostics, initializes system components, and loads the operating system from storage into memory. It plays a critical role in bootstrapping the computer system and ensuring its proper functioning. Interrupts are signals generated by hardware devices or software programs to request attention or inform the central processing unit of an event that requires immediate processing. In computer organization, interrupts enable asynchronous communication between hardware devices and the central processing unit, allowing devices to signal the central processing unit when specific events occur. The central processing unit responds to interrupts by temporarily suspending its current execution and handling the interrupt request. The firmware refers to software programs or code embedded into hardware components, such as ROM chips or flash memory, that provide low-level control and functionality. In computer organization, firmware controls the operation of hardware devices and implements essential functions such as startup routines, device initialization, and system management. It serves as an intermediary between hardware and software, providing a layer. Moore's law holds significant importance in computer organization, as it describes the trend of the number of transistors in integrated circuits doubling approximately every 2 years, leading to a rapid increase in computational power and technological advancement over time. Redundant array of independent disks configurations offer various benefits in computer organization, including improved data reliability, performance, and fault tolerance by distributing data across multiple disks and implementing redundancy techniques such as mirroring and striping. Graphics processing units enhance computer organization by offloading and accelerating graphical and parallel processing tasks from the central processing unit, enabling faster rendering of graphics, simulations, and computations in applications such as gaming, artificial intelligence, and scientific simulations. Controllers play a vital role in managing peripheral devices by providing interfaces, protocols, and control signals for communication between the central processing unit and peripherals, facilitating data transfer and coordinating operations such as data input, output, and storage. Hard disk drives and solid-state drives differ in computer organization primarily in their storage, technology, and performance characteristics. Hard disk drives use rotating magnetic disks to store data, offering larger capacities at lower cost but slower read-write speeds compared to solid-state drives, which use flash memory for faster data access. Error correction coding techniques improve data integrity in computer organization by adding redundancy to transmitted data, allowing the receiver to detect and correct errors introduced during data transmission, ensuring accurate and reliable data communication. The power supply unit is responsible for converting alternating current from a wall outlet into direct current used by computer components, providing stable and regulated power to ensure proper functioning and prevent damage to hardware components. The basic input-output system in computer organization initializes hardware components, performs diagnostic tests, and loads the operating system during the boot process, serving as a fundamental firmware interface between hardware and software. The instruction pipeline in a central processing unit enhances efficiency by breaking down the execution of instructions into multiple stages, allowing concurrent processing of multiple instructions and improving throughput and performance in computer organization. Embedded systems in computer organization are specialized computing devices designed for specific tasks or applications, such as microcontrollers in electronic appliances, automotive systems, medical devices, and industrial automation, offering compact, efficient, and dedicated functionality. Network interface cards facilitate communication in computer organization by providing interfaces and protocols for connecting computers to networks, enabling data transmission and reception over wired or wireless networks. Parallel computing in computer organization involves simultaneous execution of multiple tasks or processes using multiple processors or cores, enhancing performance and scalability in applications such as scientific computing, simulations, and data analytics. Trade-offs between performance and energy consumption in computer organization involve optimizing hardware and software designs to balance computational power and efficiency, considering factors such as processing speed, power consumption, heat generation, and battery life. Cooling systems prevent overheating in computer organization by dissipating heat generated by hardware components such as the central processing unit and graphics processing unit, using techniques such as air cooling with fans, liquid cooling with heat sinks and coolant, and thermal management mechanisms to maintain optimal operating temperatures. Expansion slots in computer organization serve as interfaces on the motherboard for adding expansion cards, such as graphics cards, sound cards, network cards, and storage controllers, allowing users to enhance the functionality and connectivity of their systems by installing additional hardware components. Firmware updates in computer organization can improve the functionality, performance, and security of hardware components by providing patches, bug fixes, and feature enhancements delivered through firmware updates. ensuring compatibility with new software, and addressing potential vulnerabilities or issues. Synchronous communication in computer organization involves data transfer with synchronized timing signals between sender and receiver, ensuring coordinated transmission and reception of data, while asynchronous communication allows data transfer without synchronized timing, relying on start and stop bits for signaling. System software in computer organization comprises operating systems, device drivers, utilities, and middleware that manage hardware resources, provide a user interface, support application software, and facilitate communication between hardware and software components. Fault-tolerant systems in computer organization enhance reliability by detecting, isolating, and recovering from hardware and software faults, employing redundancy, error detection, error correction, and failover mechanisms to ensure continuous operation and minimize system downtime. Static RAM in computer organization uses flip-flops to store data without the need for refreshing, offering faster access times and lower latency, but requiring more power and physical space compared to dynamic RAM, which uses capacitors to store data and requires periodic refreshing to maintain data integrity. The memory controller in computer organization manages data transfer between the central processing unit and main memory, coordinating memory access, addressing, and data retrieval to optimize performance, ensure data integrity, and regulate memory operations. Multi-core processing in computer organization improves performance by integrating multiple processing cores on a single central processing unit chip, enabling parallel execution of multiple tasks, applications, or threads, and increasing overall computational throughput and responsiveness. Benchmarking in computer organization involves evaluating and comparing the performance, efficiency, and capabilities of computer hardware and software components using standardized tests, metrics, and performance benchmarks to assess and validate system performance. Instruction-level parallelism in computer organization exploits parallel execution of multiple instructions within a single processor core, while thread-level parallelism involves parallel execution of multiple threads or processes across multiple cores or processors, both techniques aiming to maximize computational efficiency and throughput. Design fault-tolerant systems in computer organization involves addressing challenges such as identifying potential failure points, implementing redundancy and error detection mechanisms, minimizing single points of failure, and ensuring seamless failover and recovery procedures. Clock synchronization in distributed systems in computer organization ensures that multiple devices or components share a common time reference, enabling coordination, communication, and synchronization of distributed processes, transactions, and events across a network. Latency in computer organization refers to the delay between initiating a data transfer operation and its completion, including factors such as data transmission time, processing time, and queuing time, affecting system responsiveness, throughput, and overall performance. The addressing mode in computer organization determines how the central processing unit references memory locations during program execution, impacting the efficiency of memory access by influencing the complexity of memory addressing calculations and the flexibility of memory management techniques. Legacy interfaces in computer organization refer to older communication standards or protocols that were once widely used but have since been superseded by newer technologies, such as serial ports, parallel ports, VGA ports, and PS2 ports, which are still found on some legacy systems or devices. Bus arbitration in computer organization coordinates access to shared resources, such as the system bus, among multiple devices, ensuring fair and orderly communication by resolving conflicts and prioritizing access requests from competing devices through arbitration protocols and mechanisms. Direct memory access controllers in computer organization facilitate direct memory access by managing data transfers between peripheral devices and system memory without central processing unit intervention. improving system performance and efficiency by offloading data transfer tasks from the central processing unit. The system clock in computer organization generates timing signals that synchronize the operation of various hardware components and system processes, providing a reference for coordinating data transfer, instruction execution, and system operation. Firmware in computer organization refers to specialized software stored in non-volatile memory that controls the operation of hardware components, such as basic input-output system, unified extensible firmware interface, firmware embedded in devices, and device drivers, serving as an intermediary between hardware and software. Magnetic storage media in computer organization, such as hard disk drives and magnetic tape, offer advantages such as high capacity, low cost, and durability, but suffer from disadvantages including slower access times, mechanical fragility, and susceptibility to magnetic interference. System firmware in the boot process of a computer initializes hardware components, performs power-on self-tests, loads the operating system from storage devices into memory, and configures system settings, ensuring proper system startup and operation. Error detection and correction codes in computer organization identify and correct errors in data transmission and storage, improving data reliability and integrity by detecting and correcting errors caused by transmission noise, storage degradation, or hardware faults. The Southbridge chipset in computer organization manages input-output functions such as USB, audio, and networking, providing connectivity and control for peripheral devices and offloading input-output processing tasks from the central processing unit. Fault tolerance in computer networks involves designing and implementing redundant components, backup systems, and fault recovery mechanisms to ensure continuous operation and data integrity, minimizing the impact of hardware failures, network disruptions, or environmental hazards. The real-time clock-in computer organization tracks the current time and date, providing a reference for time-sensitive operations, scheduling tasks, and coordinating system events, even when the system is powered off. The power management unit in computer organization regulates power consumption, monitors system temperature, controls fan speeds, and manages power states to optimize energy efficiency, reduce heat generation, and prolong battery life in portable devices. Basic input-output system updates in computer organization provide patches, bug fixes, compatibility enhancements, and performance optimizations for firmware stored in read-only memory chips on the motherboard, ensuring compatibility with new hardware and software. A microcontroller in computer organization integrates a microprocessor, memory, and peripheral interfaces on a single chip, optimized for embedded systems and real-time control applications, while a microprocessor focuses solely on executing instructions and relies on external components for input-output operations. Device drivers in computer organization serve as intermediary software that enables communication between the operating system and hardware devices, facilitating their interaction and ensuring proper functionality. They translate high-level commands from the operating system into instructions that hardware components can understand, allowing the system to recognize, configure, and control various devices such as printers, graphics cards, and network adapters. Bus mastering in computer organization enhances data transfer rates by allowing peripheral devices to directly access system memory without central processing unit intervention. This reduces central processing unit overhead and latency associated with data transfer, improving system performance and efficiency by enabling faster and more efficient data transmission between devices and memory. Firmware in computer organization refers to specialized software stored in non-volatile memory that controls the operation of hardware components such as basic input-output system, unified extensible firmware interface, firmware embedded in devices, and device drivers, serving as an intermediary between hardware and software. Middleware, on the other hand, refers to software components that provide services and support for applications, such as communication protocols, database access, and distributed computing, enabling interoperability and integration between different software systems. Data serialization in computer organization involves converting complex data structures or objects into a sequential stream of bytes for storage or transmission, allowing data to be efficiently transmitted over networks, stored in files, or transferred between different systems. This process enables interoperability and compatibility between systems with different architectures and data formats. Hardware interrupts in computer organization are signals generated by hardware devices to request attention from the central processing unit, indicating that the particular event or condition has occurred, such as data arrival, error detection, or device status change. Software interrupts, on the other hand, are signals generated by software programs to request central processing unit intervention for specific tasks or operations, such as system calls, exceptions, or error handling. The Northbridge chipset in computer organization acts as an intermediary between the central processing unit and high-speed system components, such as memory and graphics cards, facilitating communication and data exchange between these components. It handles tasks such as memory access, data transfer and bus arbitration, optimizing system performance and efficiency. Clock skew in computer organization refers to the discrepancy in signal arrival times between different parts of a synchronous system, caused by variations in signal propagation delays along signal paths. It can affect the timing and reliability of synchronous communication, leading to data errors or timing violations if not properly managed or compensated for. Clock gating in computer organization involves controlling the clock signal to specific hardware components or functional blocks based on their activity or usage, enabling power savings and reducing energy consumption by disabling clock signals to idle or unused components. This technique improves energy efficiency and reduces heat generation in electronic systems, especially in low-power or battery-operated devices. The Peripheral Component Interconnect Express interface in computer organization provides high-speed data transfer and communication between the central processing unit and peripheral devices, such as expansion cards, storage controllers, and network adapters, offering increased bandwidth, scalability, and flexibility compared to traditional bus architectures. It supports features such as hot swapping, lane bifurcation, and multiple data lanes, enhancing system connectivity and performance. Hot swappable components in computer organization are hardware devices that can be inserted or removed from a system while it is running, without requiring a system shutdown or restart. This facilitates maintenance, upgrades, and repairs by allowing faulty or outdated components to be replaced with minimal disruption to system operation, improving system availability and uptime. The basic input-output system configuration utility in computer organization allows users to configure and customize basic input-output system settings, such as system parameters, boot options, hardware settings, and security features, providing flexibility and control over system behavior and functionality. It enables users to adjust system settings according to their preferences, requirements, or troubleshooting needs. Where leveling in computer organization is a technique used in solid-state storage devices, such as solid-state drives, to evenly distribute write and erase cycles across memory cells, preventing premature wear out of specific memory regions and prolonging the lifespan of the device. It improves reliability, durability, and endurance by minimizing the impact of cell degradation and extending the overall lifespan of the storage device. Error-correcting code in computer organization includes additional parity or checksum bits to detect and correct memory errors caused by data corruption, noise, or hardware faults, enhancing data reliability and integrity in memory subsystems. It provides error detection and correction capabilities, reducing the likelihood of data corruption and improving system stability and reliability. Firmware passwords in computer organization protect system firmware, such as basic input-output system or unified extensible firmware interface, from unauthorized access or tampering by requiring users to enter a password before accessing or modifying firmware settings or configurations. They enhance security by preventing unauthorized changes to critical system settings, reducing the risk of malware injection, unauthorized firmware updates, or system compromise. The chipset in computer organization serves as a central hub that facilitates communication and data transfer between various hardware components within a computer system. It includes multiple integrated circuits that manage tasks such as memory access, data transfer, and peripheral device control. The chipset acts as an intermediary between the central processing unit, memory expansion slots, and peripheral devices, coordinating their interactions and ensuring proper operation of the system. A system on chip in computer organization integrates multiple hardware components, including the central processing unit, graphic user interface, memory controller, and peripheral interfaces, onto a single chip, providing a compact and efficient solution for embedded systems and mobile devices. In contrast, a microcontroller combines a central processing unit core, memory input-output ports, and other peripherals on a single chip, offering a cost-effective and space-efficient solution for embedded applications with lower processing requirements. System firmware in computer organization refers to software stored in non-volatile memory that initializes and configures hardware components during the boot process, enabling the system to start up and load the operating system. Basic input-output system and unified extensible firmware interface are two types of system firmware, with unified extensible firmware interface offering more advanced features, such as support for larger storage devices, modern hardware interfaces, and secure boot mechanisms, compared to traditional basic input-output system firmware. The supervisor mode in computer organization is a privileged execution mode that allows the operating system kernel and system-level software to perform privileged operations and access hardware resources that are restricted to user-level applications. It provides a higher level of control and security over system resources, enabling the operating system to manage processes, memory, and hardware devices effectively. Hardware interrupts are generated by external devices to request central processing unit intervention, while software interrupts are generated by software programs to request specific services or operations from the central processing unit. The memory management unit in virtual memory systems in computer organization is responsible for translating virtual memory addresses used by applications into physical memory addresses used by the hardware, enabling efficient memory allocation, protection, and sharing among multiple processors. It manages the mapping between virtual addresses and physical addresses, handles memory protection and access control, and supports features such as paging segmentation and memory segmentation. Address decoding in computer organization is the process of determining which hardware component or peripheral device should respond to a memory or input-output request based on the address specified by the central processing unit. It involves decoding the address bus signals generated by the central processing unit to select the appropriate device, register, or memory location for data transfer or processing. Firmware in the initialization process of a computer system in computer organization performs essential tasks such as power-on self-test hardware detection and initialization, and bootstrapping the operating system. It initializes hardware components such as the central processing unit memory, storage devices, and input-output interfaces, configures system settings and parameters, and loads the operating system kernel into memory for execution, ensuring that the system is ready for use. Lock skew refers to the discrepancy in arrival times of clock signals at different components of a computer system due to variations in signal propagation delays. In synchronous communication, where data transfer is synchronized with clock signals, clock skew can lead to timing errors and data corruption. It can cause data to be sampled at the wrong time, resulting in signal distortion and communication failures. To mitigate clock skew, techniques such as clock distribution networks and clock tree synthesis are employed to minimize signal propagation, delays, and ensure synchronized operation of the system. Clock gating is a power-saving technique used in computer organization to reduce dynamic power consumption by selectively disabling clock signals to inactive or idle circuit blocks. By gating the clock signals to unused or idle circuitry, unnecessary power consumption is minimized, leading to improved energy efficiency and reduced heat dissipation in the system. This technique helps extend battery life in mobile devices, lowers operating costs in data centers, and reduces environmental impact by conserving energy. The Peripheral Component Interconnect Express interface in computer organization is a high-speed serial bus standard used to connect peripheral devices such as graphics cards, network adapters, and storage controllers to the motherboard of a computer system. It offers higher bandwidth, lower latency, and improved scalability compared to older bus architectures like Peripheral Component Interconnect and Accelerated Graphics Port, enabling faster data transfer rates and more efficient communication between devices. Peripheral Component Interconnect Express interfaces come in different versions, each offering increased performance and additional features to support evolving hardware requirements. Hot swappable components in computer organization are hardware devices that can be removed and replaced while the system is running without affecting its operation or causing downtime. They facilitate maintenance and upgrades by allowing faulty or outdated components to be replaced with new ones without interrupting system operation. Hot swappable components include storage drives, network adapters, and input-output devices, which can be replaced quickly and easily to minimize service disruptions and maximize system uptime. The basic input-output system configuration utility in computer organization is a software interface provided by the basic input-output system firmware that allows users to configure system settings and parameters, such as boot order, device settings, and hardware configurations. It provides an easy-to-use interface for accessing and modifying basic input-output system settings, enabling users to customize their system according to their requirements and preferences. The basic input-output system configuration utility is typically accessed during the system boot process by pressing a specific key combination, such as F2 or Del, to enter the basic input-output system setup menu. Synchronous communication in computer organization refers to data transfer where the sender and receiver are synchronized with a common clock signal. It ensures that data is transmitted and received at predetermined intervals, allowing for efficient and predictable communication between devices. Asynchronous communication, on the other hand, does not rely on a shared clock signal and allows data to be transmitted at irregular intervals, making it more flexible but potentially less efficient than synchronous communication. Direct memory access in computer organization is a feature that allows peripheral devices to transfer data directly to and from memory without central processing unit intervention. It offloads data transfer tasks from the central processing unit, reducing central processing unit overhead and improving overall system performance. Direct memory access controllers manage data transfer between peripheral devices and memory, using dedicated channels and buffers to facilitate efficient and high-speed data movement. The real-time clock in computer organization is a hardware component that provides accurate timekeeping functionality to the system. It maintains the current date and time even when the system is powered off by using a dedicated battery backup. The real-time clock is commonly used for time-sensitive applications such as scheduling tasks, logging events, and coordinating time-based operations in embedded systems and real-time applications. The power management unit in computer organization is responsible for managing and optimizing power consumption in the system that controls voltage regulation, power distribution, and power-saving features to maximize energy efficiency and extend battery life in mobile devices. The power management unit dynamically adjusts power settings based on system activity, workload, and user preferences to minimize energy consumption while maintaining optimal performance and reliability. Firmware updates in computer organization can impact the functionality and performance of hardware components by introducing bug fixes, security patches, and new features. They're typically provided by hardware manufacturers to address known issues, improve compatibility with new software, and enhance the overall reliability and usability of the hardware. Firmware updates are installed using specialized software tools provided by the manufacturer. It may require rebooting the system to apply the changes. Clock gating is a power-saving technique used in computer organization to reduce dynamic power consumption by selectively disabling clock signals to inactive or idle circuit blocks. It helps conserve energy by shutting down clock signals to unused or idle components, reducing power consumption without affecting system functionality. Clock gating is commonly used in digital circuits, processors, and integrated circuits to improve energy efficiency and extend battery life in mobile devices and data centers. The peripheral component interconnect bus in computer organization is a high-speed interface used for connecting peripheral devices to the central processing unit and main memory. It provides a standardized communication protocol for transferring data between the central processing unit and peripheral devices, such as network adapters, graphics cards, storage controllers, and sound cards. The peripheral component interconnect express bus supports plug-and-play functionality, allowing devices to be added or removed dynamically without requiring system rebooting, and offers high bandwidth and low latency for efficient data transfer between devices. Peripheral devices communicate with the central processing unit in computer organization through various interfaces and protocols. These interfaces, such as USB, Ethernet, SATA, and Peripheral Component Interconnect Express, facilitate data transfer between the central processing unit and peripheral devices. Each peripheral device has its own controller or interface circuitry that translates data between the device's format and the format understood by the central processing unit. Through these interfaces, peripheral devices can send and receive data, commands and status information to and from the central processing unit, allowing users to interact with the computer system. Interrupt requests facilitate communication between devices in computer organization by allowing peripheral devices to request attention from the central processing unit. When a peripheral device requires central processing unit intervention, it sends an interrupt request signal to the central processing unit, signaling that it needs to be serviced. The central processing unit then temporarily suspends its current operation, saves its state, and executes an interrupt service routine to handle the request. Interrupts enable efficient multitasking and asynchronous communication between devices, allowing the central processing unit to respond to time-critical events in real time. The system bus in computer organization is a communication pathway that connects various components of the computer system, including the central processing unit, memory, and peripheral devices. It provides a means for data transfer between these components, enabling them to exchange information and coordinate their activities. The system bus typically consists of multiple parallel conductors or traces that carry address, data, and control signals between different components of the system. Clock speed affects the performance of a central processing unit in computer organization by determining how quickly it can execute instructions and process data. A high clock speed allows the central processing unit to perform more instructions per second, resulting in faster overall system performance. However, increasing the clock speed also leads to higher power consumption and heat generation, which may require additional cooling measures to maintain system stability. The memory controller in computer organization is responsible for managing data transfer between the central processing unit and memory modules. It controls the flow of data between the central processing unit and memory, including fetching instructions and data from memory, writing data back to memory, and coordinating memory access operations. The memory controller plays a crucial role in optimizing memory performance, ensuring efficient data transfer rates, and maintaining system stability. As we conclude today's exploration of computer organization, we hope you've gained valuable insights into the foundational principles that drive modern computing systems. Don't forget to subscribe to Loops and Loops for more captivating content on computer organization, computer architecture, and emerging technologies. Let's continue to loop in new knowledge, innovate with computing systems, and shape a future where technology continues to evolve at an exponential pace. Until next time, keep those loops tight, keep exploring, and keep pushing the boundaries of what's possible with computer organization.